Assalamu alaikum students, this is Zishan Ahmed again from SLS Montessori and School. In our previous video we did first two theorems of chapter number 16 that were regarding areas of parallelograms. Now the rest of the two theorems of 16 chapter are areas of triangles. So what is saying this 16.1.3? The statement is saying triangles on the same base and of the same or equal altitudes are equal in area. In the diagram we are having two triangles. The first one is A, B, C and the second one is D, B, C. You can see both triangles have same base B, C. So read what is given. Triangles ABC and DBC on the same base BC and having equal altitudes. What is to be proved? We have to prove that triangles are equal in area. So area of a triangle ABC, this is ABC, and area of triangle DBC. Both triangles have same area, equal area. Construction. Draw BM parallel to CA. This is BM. We have to draw BM parallel to CA and CN parallel to BD. This P means parallel. CN parallel to BD. This is CN. This is CN parallel to BD. Meeting AD produced in MN. Produced this line D to the right side till N and produce this A to left side till it meets N. Okay, now we are going to move it. Now students, we move to its proof. In the proof, this is written as triangle ABC and triangle DBC are between the same parallels. Why they are between the same parallels? Because their altitudes are equal, which was given in the statement. Hence, MADN is parallel to the line BC. Yes, you can see MADN. This is a straight line which is parallel to BC. Now, if you look into the diagram, this is B, C, A, M. This is now a parallelogram. Why it is a parallelogram? Because we know that AM and BC, these both lines are parallel. And in the construction, we said that MB is parallel to CA. So all of the sides, opposite sides are parallel, hence it is a parallelogram. With the same arguments, if we look at the figure B, C, N, D, it is again a parallelogram because this DN and BC are parallel, and in the construction we also said that this CN is parallel to BD, which means this is another parallelogram. And if you look another thing, that these two both parallelograms are having same base, that is BC. So by using the theorem 16.1.1, in which the statement was two parallelograms on the same base and in between the same altitudes are equal in area. So these are the two parallelograms with same base and in between the same altitudes. So area of a parallelogram BCAM will be equal to area of a parallelogram BCND. So this is equation 1. I gave the reason that by using the theorem that parallelograms are on the same base BC and between the same parallels. Now again, if you look into this diagram, this is parallelogram BCAM and this line AB over here is behaving as its diagonal, and diagonal always splits a parallelogram into two congruent triangles. I mean to say that this AB will split whole this parallelogram into two congruent triangles. First triangle is ABM, second one is ABC. And I can also say that area of this whole parallelogram will be equal to 2 times of area of triangle ABC, or area of triangle ABC is equal to half of the area of parallelogram BCAM. This is equation 2. We can also write, if we shift this 2 to the left side, it will multiply with the area of triangle ABC, and equation will become 2 into area of triangle ABC is equal to area of parallelogram BCAM. That means area of a parallelogram is equal to 2 times of a triangle ABC. Using the same argument, we can say the same thing about the second parallelogram, which is B, C and D. Over here CD is behaving as diagonal, so this CD will split whole this parallelogram into two congruent triangles. Triangles will be N, C, D and D, B, C. So over here I can write area of triangle DBC will be equal to half of the area of parallelogram BC and D. And with the same argument that if we bring this 2 to the left side of this equality, this 2 will multiply with the area of triangle DBC, and equation will become area of parallelograms BC and D will be equal to 2 times of the area of triangle DBC. What is the reason of these both? That I told you that each diagonal of a parallelogram bisects it into two congruent triangles. Now if I put both equations 2 and equation 3 in equation 1, it will be area of parallelogram BCAM. By using equation 2, I am replacing it by 2 times of area of triangle DBC, like this, 2 times of area of triangle ABC, and on the right hand side it is area of parallelogram BC and D. I use the equation 3 and I am replacing it as 2 into area of triangle DBC. 2 and this 2, both 2's will be cancelled from left hand side and right hand side of this equality, and we will be left with area of triangle ABC is equal to area of triangle DBC. This was to be proved and this has been proved. Okay students, now we are going to do the last theorem of chapter number 16, and the statement of this theorem is triangles on the equal bases and of the equal altitudes are equal in area. In the previous theorem 16.1.3, we have done that triangles on the same base. So there is a slightly difference in it, that in the previous 16.1.3 we were having triangles on same base, but right now in 16.1.4 we are having two triangles on equal bases and of the equal altitudes are equal in area. What is given? Triangles ABC and DEF are on equal bases BC and EF and having equal altitudes. Both triangles are having equal altitudes. So looking in the diagram, this is a triangle A, B, C with the base BC, and the second triangle is D, E, F with the base EF. Given that both triangles have equal bases, so we can say that this BC is equal to EF. What we have to prove is that both triangles are equal in area. I mean that area of triangle ABC is equal to area of triangle DEF. Moving to the construction. Place the triangles ABC and DEF so that their equal bases BC and EF are in the same straight line and their vertices on the same side of it. You can see that this is BC, EF. This is a straight line. Now draw BX parallel to CA. This is BX. We are drawing BX parallel to CA. This is CA. And FY parallel to ED. This is FY, and we are drawing parallel to ED, meeting AD produced in X and Y respectively. So this is meeting at X. If we produce A to the left side, it will meet at X, and from D, if we move to the right side, it will meet at y. Okay students, now we move to its proof. Looking in the proof, what we have, triangles ABC and triangle DEF are between the same parallels. Yes, of course, because their altitudes are equal. So XA dy is parallel to BCEF. Yes, if you look in the diagram, this is XA dy. This is a straight line which is actually parallel to BCEF. This BCEF is another straight line. So these two lines are parallel. Now if you look into this figure, this is BCAX. This is again a parallelogram. Why that is a parallelogram? Because XA and BC, these both lines were already parallel, and in the construction we have drawn that XB parallel to AC. So all opposite sides are parallel. That's why we are saying that this BCAX has now become a parallelogram. Using the same arguments, we can say EFYD is another parallelogram, because DY and EF were both already parallel, and FY we have said in the construction that this is parallel to DE. So similarly, all of the opposite sides are parallel in this figure. So EFYD, this is another parallelogram. And area of parallelogram BCAX and area of parallelogram EFYD both are equal. Why? We are using the statement of theorem 16.1.2, in which statement was saying two parallelograms on equal bases and in between the same altitudes are equal in area. So this is BCAX, this is a parallelogram with the base BC, and EFYD is another parallelogram with the base EF, and we know that BC is equal to EF. Why BC is equal to EF? Because these two are the bases of given triangles. And this is given in the statement that both triangles are having equal bases. So now we can say that area of parallelogram BCAX is equal to area of a parallelogram EFYD. Okay students, as we did in the previous theorem 16.1.3, now if we look this line AB, this AB is behaving as diagonal of a parallelogram. As we know that, I told you in the previous theorem that diagonal of a parallelogram always bisects that parallelogram into two congruent triangles. In other words, same thing that I have written in the previous theorem, that area of triangle ABC is equal to 1 by 2. I mean half of the area of parallelogram BCAX, and if this 2 is shifted to the left side of the equality, the equation will become 2 times of the area of triangle ABC is equal to area of a parallelogram BCAX. We say it equation 2. Using the same arguments, we can say the same thing about the second parallelogram, that is EFYD. In this DF is behaving as diagonal, so it will split this whole parallelograms into two congruent triangles, and in other words, I can also say that area of whole this parallelogram will be equal to 2 times of area of triangle DEF. So I have written in this equation 3 that area of triangle DEF is equal to half of the area of parallelogram EFYD, and on the same argument that if we shift this 2 to the left side, the equation will become 2 times of the area of triangle DEF is equal to area of parallelogram EFYD. What is the reason? I told you that each diagonal of a parallelogram bisects it into two congruent triangles. Now again, as I used to put both equation 2 and equation 3 in equation 1 in the previous theorem 16.1.3, so I will do the same thing. I am using equation 2 and equation 3, and I will replace the values of these two, area of parallelogram BCAX and area of parallelogram EFYD. So if I look the left side, area of parallelogram BCAX. Look at the equation 2. Area of parallelogram BCAX is equal to 2 times of area of triangle ABC. So this equation 1, the left side of equation 1 will be replaced actually by 2 times of area of triangle ABC. Similarly, the right side of this is containing area of parallelogram EFYD, and if we look in the equation 3, area of parallelogram EFYD is equal to 2 times of area of triangle DEF. So right hand side will be replaced by this 2 times of area of triangle DEF. This 2 and this 2 both will be cancelled from left hand side and right hand side of this equality. And what we'll have, area of triangle ABC is equal to area of triangle DEF. This was to be proved. After proving both of the theorems of triangles, now we are solving a question of 16.2. The question says, show that the median of a triangle divides it into two triangles of equal area. So we need to draw a triangle first. This is a triangle A, B and C. And the next one, we need to draw its one median. Median start from a vertex and intersect, and in fact bisect the opposite side. So this is AO is a median, as AO is bisecting the side BC. Bisecting means O is the midpoint of the side B, and C, which also means further means BO is equal to OC. Now read the given. In the triangle ABC, AO is the median and BO is equal to OC. This is obvious, as because AO is the median. To prove is, area of a triangle ABO, this is ABO, this is triangle area, and is equal to area of triangle ACO. The second one is AC, this is C and this is O. This is the second area. So we need to prove the equality, that area of triangle ABO is equal to area of triangle ACO. In the construction, we are draw CE parallel to BC. This is, draw DE parallel to BC. This is D and this is E. So this is the straight horizontal line we are drawing parallel to this BC. Further, draw PC parallel to AO. This is AO, this is AO, this is PC. So we are drawing this PC parallel to this AO and QB parallel to AO as well. So on this side we are drawing this QB parallel to AO. Now moving to the proof. AQPO is a parallelogram. This one, AQBO is a parallelogram. Yes, because AQ and OB both are parallel to each other, and QB and AO are parallel to each other as well, that we have drawn in the construction. So we can say AQBO is a parallelogram. Construction. Similarly, APCO is a parallelogram as well. In the construction that we have drawn this AP parallel to OC and PC parallel to AO. So we can say it as well that APCO is a parallelogram. Now since AO is the median of this triangle, median means this AO is bisecting this BC, and bisecting is further we mean that BO is equal to OC. So BO is equal to OC. Now if you observe, this is a parallelogram AQBO, and second one is APCO. Both parallelograms are having equal bases and having equal altitude, so both will be equal in area. So we can write area of parallelograms AQBO is equal to area of a parallelogram APCO. Again, as this is behaving, this AB is behaving as diagonal in this parallelogram, and AC is behaving as diagonal in this parallelogram. And we know in the theorem we did this, that diagonal of a parallelogram always bisects it or divides it into congruent triangles. So we can write area of a parallelogram AQBO. We can replace this by 2 times of area of triangle ABO. This whole can be written 2 times of just ABO. Similarly, this can be written, this whole, this ABCO parallelogram whole can be written as twice than ACO, like this. And this 2 and this 2 will be cancelled with by each other, and we will be left with just area of triangle ABO is equal to area of triangle ACO. So students, like this we have proved that median of a triangle divides it into 2 triangles of equal area. So we are done with chapter 16 as well. Take care of yourselves. Thank you. Allah Hafiz.